Okay, so welcome, ladies and gentlemen, and thanks for tuning in for our fourth session on the virtual conference on epistemic uncertainty and engineering. It's a collaboration with the Institute for Risk and Uncertainty, the University of Sheffield, on the DigiTwin program that's been sponsored by UKRI, and we've also received new sponsorship from, apologies, I've got the wrong slides here as well. We've got a new sponsor from the SRA as well, the Society for Risk Analysis. Here we are. Yeah, we've added in the logo now. And our topic for today will be kinds of uncertainty with Professor Yakov Ben-Haim and Dr. Francois Hemez. So the schedule for the coming sessions, our next talk will be on the 3rd of March on uncertainty engineering with Daniel Straub and Louis Crespo. And then the one after that will be on the 12th of March. So make sure to write that in your diaries. So the agenda for today, our first speaker will be Professor Yakov Ben-Haim, and he'll be speaking on innovation dilemmas and Infogap perspective, 45 minutes, and then followed by Q&A. And then to follow that, Dr. Francois Hemez will be speaking to us about uncertainty in numerical simulations. Does it matter? Again, followed by Q&A, and then we'll have an open discussion where there'll be fist fights and fireworks and all sorts of debate around are there other kinds of uncertainty, and that'll be roughly 30 minutes. It might overrun, but obviously we're scheduled in to speak for 30 minutes, and everything will be recorded, so you can check back these talks at your own leisure. So I'd like to introduce our first speaker. So Professor Yakov Ben-Haim initiated and developed an Infogap decision theory for modeling and managing deep uncertainty. Infogap Theory is a decision support tool providing a methodology for assisting in assessment and selection of policy, strategy, action, or decision in a wide range of disciplines. The theory has impacted the fundamental understanding of uncertainty in human affairs and is applied in decision-making by scholars and practitioners around the world in engineering, biological conservation, economics, project management, climate change, natural hazard response, national security, medicine, and other areas. I mean, I think that pretty much covers most areas, but there's more still. He's been a visiting scholar in many countries and has lectured at universities, technological and medical research institutions, public utilities, and central banks. And he's published more than 100 articles in 6 books. He's currently the professor of mechanical engineering and holds the Yitzhak Modai Chair in Technology and Economics at Technion, Israeli Institute for Technology. So thank you very much for coming, and please enjoy the talk. If you could share your slides, Yakov, that'd be great.
Okay, it says you cannot share a screen while the other participant is sharing, so you have to unshare. There we go. Okay. So do you see my first slide there?
Yeah, we do.
Okay, good. So good afternoon or good evening or good morning or whatever it is. I'm going to tell you about innovation dilemmas. Let's see now, how does this work here? Does this work here? Yes, so we'll start by discussing what is an infogap, and then we'll delve into more theoretical discussion of innovation dilemmas and proceed to an example of seismic safety. And if we have time, I'll briefly overview a number of other applications of infogap theory. So what is an infogap? This gentleman on the left is very commonly known as Lewis Carroll, and he wrote a book of mathematical riddles called Pillow Problems. The last riddle in that book is called Transcendental Probability, and it is stated as follows. A bag contains 2 counters as to which nothing is known except that each is either black or white. Ascertain their colors without taking them out of the bag. Now, you can't determine their colors. You don't have enough information. You face an info gap, a deep uncertainty. Of course, Lewis Carroll can prove anything, and he proves that one is black and one is white, but he cheats. On a more practical level, in 1953, the Thames estuary, the Thames River, experienced its worst storm surge of the century. flood defenses were breached, 300 people died, Canvey Island in the estuary was devastated, and a new barrier system was opened in the auspicious year of 1984. And more recently, a Thames 2100 program has been promoted for redesigning the flood defenses, and they are facing deep uncertainties. For example, they have fairly complete statistics for surge heights for the last 200 years, but they want to plan for a once in 1,000-year surge. They don't have the data. And anyway, the next 1,000 years is going to be different from the last 1,000 years because of global warming and tectonic settling and human action. These are deep Knightian uncertainties, the economists would call them. These are infogaps. We've heard about Fukushima again fairly recently, not as tragic as in 2011, but 2011 was an example of an infogap. Not only can you not predict when a Richter 9 earthquake will occur and whether it will be accompanied by a tsunami, but the interactions between organizations and institutions, the constraints imposed on those institutions and how they will impact their response, those are infogaps that severely and adversely influenced the evolution of that event. Managing mobile networks. We all have cell phones, but somebody has to allocate the resources among those cell phones as we move around, encounter barriers, chat with our neighbors, and the infogaps that the resource allocation faces are quite severe. Climate change is another wonderful area for infogaps. Greenhouse gases result in temperature rise, which has adverse economic impact. We can model the impact of greenhouse gases on global mean temperature, and we can model the impact of global mean temperature on economic activity. The trouble is, those models are highly uncertain. The data is controversial. And just as one minor example from a International Panel on Climate Change report from some years back, here is a plot of 10 different models of the climate sensitivity parameter, probability distribution for the climate sensitivity parameter, 10 different models from 10 different distinguished academic institutions. They're all very different. You're the decision maker, you're the planner. You face an infogap. In summary, an infogap is a Knightian uncertainty in economic parlance. It's a disparity between what we do know and what we need to know to make a responsible decision. So there's two elements here. There's the element of ignorance and how that ignorance bears on the decisions that we need to make. We're not going to do a lot of math in this talk, and hardly any actually, but we will show a few infogap models of uncertainty in which we will see that they are unbounded family of sets of events. No known worst case. The starting point for infogap analysis is you think things are bad now, they can get worse. We don't know a worst case, and we don't know probability distributions on the uncertain entities. What sorts of uncertainties can we confront? Well, there can be uncertainties in functional relationships. For example, the future spatial temporal loading patterns on a structure can be uncertain. Stress strain curves of new materials, SN load lifetime curves are difficult to determine and change over the life of the structure. Crack shapes. Cracks have wonderful shapes, but they're always different. Probability distributions are very useful, but often we are uncertain about them, especially about the tails of those distributions. So infogaps can be in uncertainties in the shape of a function. There can be uncertainty in the mechanisms by which processes proceed, uncertain or unknown synergistic effects, nonlinearities. In some situations, we will confront adversarial behavior in which each adversary acts strategically. That is, he knows that I know, that he knows that I know, and that mutual knowledge influences in an uncertain and highly unknown way the actions of all the adversaries. On the most prosaic level, there can be uncertain parameters. We simply don't know the Young's modulus or the Poisson ratio. We don't know the cost of materials or how much time it's going to solve that problem that's bugging us. We don't know the probability of failure. We don't know parameters of a probability distribution. So there are many different types of infogaps, functional relations, mechanisms, and parameters. This talk is about infogap theory and its applications, as we will shortly see. But it's important to understand when you do not need to use infogap theory. If you reliably know probability distributions, then I, Yakov Ben-Haim, will be the first to say that you should not use infogap theory. So the first question you ask is, do I reliably know probability distributions? And if so, forget infogap. If there is uncertainty in your probability distributions, or if you don't know probability distributions at all, then infogap can be useful, as I hope to show in the continuation of this talk. So that was a brief overview of what I mean by an infogap. And now let me tell you what I mean by the idea of an innovation dilemma. We have to choose between two options. The first option is some innovative new concept, some bright idea, some young graduate student has invented something wonderful. It's very promising. It promises to be better than anything we've got, but because it's new, we are unfamiliar with it, and its implications are unknown, and we face a high level of uncertainty, as opposed to the second option, which we could choose, which is, let me call it, the state of the art. It's really very good. It's what we use. It works. It's not as good as the innovative new concept, but we're more familiar with it, and so there is lower uncertainty. The dilemma, the innovation dilemma, is that what is innovative is more uncertain, but promises to be better. And my goal in this talk is to characterize that dilemma in a quantitative way and provide a mechanism for making a decision, for resolving the dilemma. Let me just give a few examples of innovation dilemmas. Automotive collision control, we're hearing increasing attention given to automatic control of automatic steering and control of automobiles. That's still considered an innovative option, as opposed to the reliable, old-fashioned, hand-operated and air-controlled braking system and steering system. Chemical safety. In many industries, we have dangerous chemicals that we can monitor by distributed sensors that are connected in various ways to a central controller, or we can do on-site inspection. One is more innovative, probably more informative, but also perhaps newer and more uncertain than state-of-the-art on-site inspection. Peace or war. Sadat came to Jerusalem in 1978. That was a bold diplomatic initiative, definitely an innovation, as opposed to state-of-the-art, if you want to call it that, of conventional diplomatic military cycle that had characterized Egyptian-Israeli relations until 1978. Tremendous uncertainties in Sadat's innovation, and unfortunately, he paid for them with his life 4 years later. Oops. And nurturing economic growth in the third world. The innovative approach is to nurture human capital, educate people, train them how to run their, whatever it is they're trying to run, in more effective manners. Or the state of the art traditionally has been to import technology, import infrastructure, and sort of lay that on top. The innovative is presumably putatively better, but it has tremendous uncertainties because of cultural disparities. Financial investment. A new startup firm, a venture capital firm, is innovative, promises to make lots of money, but it's more uncertain, certainly, than US Treasury bonds. To summarize these innovation dilemmas, it's risk-taking or risk-avoiding. Nothing ventured, nothing gained. That's the innovative motto. Nothing ventured, nothing lost. That would be the conservative state of the art. And the dilemma of choosing between these two approaches is the dilemma that I want to explore in my talk. So let's consider strategies for dealing with an innovation dilemma. The most common strategy for decision-making in general, I will refer to as outcome optimization. We have a range of options, we have models and data and knowledge, and we use that information to predict the outcome of each of the options. And you adopt the option that is predicted to be best. You optimize the predicted outcome. The trouble, of course, is that if your models and data are wrong, then your predictions are wrong, and so your choice is probably going to be unsatisfactory. Min-max, by which I mean maximize the minimum reward, is an idea that goes back at least 70 years to Abram Wald in the 1940s, and implicitly even before that. In this case, you identify a worst case and you make the worst case as good as possible. This is a worst case avoiding catastrophe approach. And its vulnerability, of course, is that worst cases are usually what we know least about. And so to focus our entire decision, to hinge or pivot our decision on that part of our knowledge, the worst case, about which we know least, is perhaps a risky, unreliable, maybe even irresponsible approach. Let me qualify that. If you do know the worst case, then perhaps min-max is suitable. But if the worst case is just some sort of guess, then it may not be a good strategy. The idea that I'm going to be developing in the coming moments is the idea of robust satisficing. In this case, what we will see, and I will elaborate on this considerably, is what we are optimizing is robustness to uncertainty. And satisficing means satisfying a critical requirement. So in this case, we're not trying to optimize an outcome like the first option, or optimize a worst case like in the second. What we're optimizing is our immunity to our ignorance. Of course, there are vulnerabilities here as well, as we will see. The flip side of robust satisficing is opportune windfalling. The windfaller says, let's try and get something better than anticipated. Let's see if we can choose an option which is opportune for exploiting opportunities, for exploiting better than anticipated scenarios. We're not going to talk about that very much, but it is a very useful approach in some situations. We will see very briefly an example of opportune windfalling. So I've outlined or briefly mentioned 4 decision strategies: outcome optimization, max-min, robust satisficing, and opportune windfalling. And the question, of course, is which should one use? And that depends on what you know and what you don't know. As I stated a moment ago, if your models and data are pretty good, then probably outcome optimization is the way to go. If you know a worst case, if you can reliably identify worst scenarios, then perhaps min-max is the way to go. When your uncertainty, when your infogap is really deep, then perhaps robust satisficing is the way to go. The attitude there being, you ask yourself, what's the worst outcome you could live with? You try and satisfy that requirement, and what you optimize is your robustness to your ignorance. We will develop that idea now. So, robust satisficing and innovation dilemma. Again, we have to choose between 2 options. A1 is an innovative option, very promising, but it's new and we're unfamiliar with it, and it has higher uncertainty. A2 is state-of-the-art, works fine. It's not quite as good as these new ideas that these young people are coming up with all the time, but there's less uncertainty with A2. How do we choose? Well, first of all, let's characterize the innovative option A1. The horizontal axis here is the quality of the outcome, where to the left is good and to the right is poor. Presumably small is good. Maybe we're talking overdraft or something like that. So we are able to use our knowledge and our information to predict an outcome of the innovative option, indicated by the arrow on this graph here. And we're also able to use our information to predict the outcome of the state of the art, which is also acceptable, let's say, but not as good as the innovative option, which is why, of course, we're considering the innovative option. So A2 is good, but not as good as the predicted outcome of A1. If we're ignoring uncertainty for the time being, or to state that in a positive way, we're using our best knowledge, our best understanding, our best data, and based on that best information, A1 is better than A2, the innovative is better than the state of the art. One might tend to think that A1 should be adopted. But it's more uncertain, which is, of course, the crux of our issue here. So now let's begin to consider uncertainty, where the horizontal axis is the same as before, and I've added a vertical axis, which is the degree horizon of uncertainty, I'm calling it. And we are considering the worst outcome at a small level of uncertainty. When you have a small level of uncertainty, the worst possible outcome is not as good as your predicted outcome, because with some uncertainty, some things could go wrong, and so the worst is a bit less desirable than the putative predicted outcome. And as we add more uncertainty, go up to medium and high uncertainty, we're able to plot out a curve of the worst possible outcome on the horizontal axis versus the horizon of uncertainty on the vertical axis. This curve then characterizes the interaction between uncertainty and how bad things could come out based on the innovative option A1. And now the curve on the frame on the left is the same as what we just saw. On the right, it's also the same picture, but I'm relabeling the axes. I'm now calling the vertical axis robustness to uncertainty, and the horizontal axis maximum tolerable damage. And now I'm going, and in the right-hand frame, we are examining it from the horizontal up to the curve and across to the vertical, unlike what we did on the left-hand frame, where we looked at a degree of uncertainty and then down to the worst outcome. It's the same curve, but I'm giving it a different interpretation now. Now this curve is the robustness curve. It is the maximum tolerable damage for any given level of robustness to uncertainty. And the first thing that we need to understand in this robustness curve is a fundamental and irrevocable trade-off. The positive slope of this curve expresses a trade-off between robustness and performance. As we demand better performance, as we become stricter in our performance, moving to the left on the horizontal axis, as we move to the left on the horizontal axis, we are forced down on the vertical axis. Robustness trades off against performance. That's sometimes called the Pessimist Theorem. Any healthy pessimist knows that you are more vulnerable to uncertainty. Your robustness is lower as your demands become more demanding. The other thing to note in this curve is what I will refer to as cost of robustness. We can see that the slope is not constant on this hypothetical curve, and at the upper end of the curve, the slope is fairly low. In other words, we have to move quite a bit to the right, foregoing a lot of performance to gain anything vertical. The cost of robustness, especially at the upper end of this curve, is rather large. We have to forego performance in order to garner robustness to uncertainty. So how do we evaluate and choose between the innovative and the state of the art? We compare the robustness curves. So this frame shows the robustness curve of the innovative option A1, exactly as it was before, with the robustness curve of the state of the art A2, where the state of the art is predicted to be worse. But in this particular formulation, because the state of the art is less uncertain, its cost of robustness is lower. The robustness curve for A2 is steeper. In other words, one can buy robustness in exchange for foregoing performance at a lower price in terms of performance with A2 than with A1. And what we see here in this curve is that the innovative A1 option is more robust than the state-of-the-art at low levels of tolerable damage further to the left, whereas A2 is more robust than A1, and A2 is thus robust preferred if you're not quite as performance requiring when you're to the right of the intersection. In other words, the innovation dilemma here, and this is graphically the crux of the issue, the innovation dilemma is expressed by the intersection of the robustness curves. A1 is putatively better. Its predicted performance is far to the left, very small damage, but the robustness far to the left is very low. A2 is not quite as good. Its predicted outcome is more to the right. And the dilemma is that one is more uncertain than the other, and we face a preference reversal. The dilemma is not resolved unambiguously for one or the other, for A1 or for A2. The dilemma is resolved depending on what level of performance you require. If your required performance is to the left of what I've labeled as D cross, then the innovative option A1 is more robust and then hence robust preferred, although caution is required because the robustness may be low. In the example that we'll address shortly, we will talk about low and high robustness. The preference reversal reverses to option A2 if one's performance requirements are more lenient, if you're further to the right, if you're to the right of D cross. The preference reversal is the resolution of the dilemma expressed by the crossing robustness curves. So let's look at a more concrete example to try and solidify these ideas. I want to design a structure for seismic safety. I want a seismic resistant structure. I want a structure that is robust to load uncertainty because there have been many earthquakes, but the next one is going to be different from the last one. There are a number of questions that we're going to have to face. More robustness is better than less robustness, but how much robustness is enough? How safe is safe enough is a classical question. We're going to confront that question here as well. In a somewhat different form, we'll ask the question, what is the value of an increment of robustness? If I'm able to increase the robustness by a certain quantitative amount, what does that mean qualitatively? What are the design implications? So those are questions that we will touch on, although briefly. The Infogap analysis of robust satisficing entails three components. The first component is what we will refer to as the system model. In this seismic example, that will probably be the structural dynamics of the system that we're concerned with. The second component in the Infogap analysis of robustness is performance requirements. There may be multiple performance requirements. We may require that displacements between floors not exceed a critical value. We will consider other performance requirements also. The third component in the Infogap robust satisficing analysis is the Infogap model of uncertainty. We will look briefly at a few Infogap models shortly. Once we identify these three components, the system model, the performance requirements, and our Infogap models of uncertainty, we ask the question of robustness. What is the maximum horizon of uncertainty up to which all the uncertain entities, loads, for example, satisfy the performance requirement for the design in question? How immune are we? How robust are we to uncertainty in the system characterized by the system model and the performance requirements? Let's look briefly at a few system models. in this case, U of t is a load function varying over time. U tilde is our best estimate of a load function. U is the unknown true load function. And this Infogap model of uncertainty is a set of all functions, U of t, whose mean square deviation from the anticipated load is bounded by some horizon of uncertainty h. The energy-bound model, as this model is called, is very good for dealing with functions which are subject to severe transience, so that U can deviate very greatly from U tilde for short periods of time. That is suitable for some situations such as seismic loads. Another type of Infogap model is the envelope-bound model. In this case, U deviates from U tilde no more than the horizon of uncertainty. In this case, as distinct from the energy-bound model, large transients are not allowed, but persistent transients are included in the envelope model, unlike in the energy-bound model. I need to stress also that Infogap models are not a single set, but they're a family of nested sets, as I think I mentioned earlier. So the value of h, the horizon uncertainty, is not known. The Infogap model is not a single set of unknown functions. It's a family of nested sets. There are many types of Infogap models. Here's just one more. We may have spectral information where the Fourier coefficients are uncertain in one or another ways. And there are many other types of Infogap models. How do you choose an Infogap model? As the Lord High Executioner said in Gilbert and Sullivan's Mikado, let the punishment fit the crime. Let the Infogap model fit your ignorance. So getting back to the seismic structural design problem, the system model may be dynamic displacements between points in the structure, or perhaps time to recovery. If we're talking about residential buildings, if time to recovery is a day or two or a week or two, those are very different situations. There may be monetary considerations and other functions that are elements of our system models. For each system model, in this example, there are corresponding performance requirements. We may impose a requirement that the displacement between floors in the structure not exceed a critical displacement. We may require that the time to recovery not exceed a critical time, or costs not exceed critical costs. These equations 10, 11, 12, these are satisficing requirements. We are not trying to minimize displacement or minimize time to recovery or minimize cost. We're trying to satisfy critical requirements on those entities, and we will maximize robustness. The problem, of course, is that the system model depends on the load function, which is highly uncertain. There may also be other uncertainties. I will refer only to load functions. There can be uncertainties in material properties and other elements. So the robust satisficing strategy is satisfy the performance, maximize the robustness. And we need to pause just briefly and stress we're not trying to optimize performance. And when your boss says, Yakov, do the best you can, and then I say, well, I'm actually only trying to satisfy, make an adequate outcome, he may squint at me or even fire me, but then I'll quickly hasten to explain to him that we are optimizing something. We're optimizing the robustness to our ignorance. Now, robustness is not a substantive entity, but it is important when you face deep uncertainties. There are lots of examples of this seismic development and others, of course, in infogap.com. If we go a little bit further into the seismic example, I want to distinguish or choose between two design concepts. Seismic resistant structure, where the basic idea is stiffness. Build a stiff structure, a strong structure that can resist seismic loads, as opposed to a different design concept, base isolated structure, which in a sense floats. It of course doesn't really float, but it is base isolated to some extent, and so it is insulated to some degree from the seismic loads, and our performance requirement is that the time to recovery be acceptable. Another equation, just to show that we've got equations here for those who, the many among you who love equations. The robustness is the greatest maximum horizon of uncertainty H, up to which the time of recovery is acceptable for all uncertain loads. The evaluation of the robustness function doesn't concern us at this point. It's actually not difficult in this problem. There is a publication here with Kano and Fujita, two Japanese colleagues. And one can evaluate robustness curves for the two design concepts, seismic resistant structure and base isolated structure. And the base isolated, this is the dashed curve, is putatively better, but the predicted outcome of the base isolated structure has zero robustness. The seismic resistance structure is not predicted to be as good, but again, the robustness of that prediction is zero. Choosing between these two design concepts based on these predictions is fatuous because those predictions have zero robustness. We want to climb up the robustness curves and exploit the trade-off between robustness and critical time to recovery, and choose an option that has large robustness or large robustness at an acceptable time to recovery. Yes, okay. And again, like in the abstract example that we discussed earlier, we see a preference reversal. So that the dashed curve, that's the base isolated, has a robustness of 1, which is fairly large robustness. We won't get into that for lack of time. Has a robustness of 1 or a bit more than 1, and is more robust than the seismic resistance structure, but the SRS has vastly greater robustness if we're willing to accept somewhat larger time to recovery. Okay, there are lots of other examples. We're really pretty much out of time, I think. Boss, maybe we have a few more minutes. Let's look at a few examples quickly. Here is a flood defense example studied by Professor Jim Hall at Oxford, and one of his, I think he was a PhD student at the time. The left curve shows robustness curves versus net present value of the investment. And we see that the in this case, values to the right are desirable, values to the left are less desirable. And so the green option, the green dashed option, is most robust over much of the range, although it may not be feasible for various implementation reasons. We see that the black has preference reversal both with the green and the blue. So we're seeing phenomena like we saw before. The curves on the right are opportunist curves. And here we're asking for net present values that are better than anticipated. And we see that the green is much more opportune than the blue and much more opportune than the black. If we were ambiguous a little bit, say we're in the range in which the robustness of the options are more or less similar, we might break the tie using the opportunist, which is unambiguous. More Japanese colleagues have studied robustness of multidimensional truss structures. Work with my colleague who will address you shortly, Francois Hemez at Los Alamos, dealing with nonlinear dynamics, transients in nonlinear dynamic materials. Very complicated experimentally, and the question is, how do you draw inferences from limited experimental data? applications in explosive materials for which you have limited experimental abilities. You don't like blowing up your laboratory. Neural nets. This was an interesting work by UK colleagues a number of years ago, evaluating the design of neural nets given uncertainty in the training data. This is an important problem because the training data is likely to be quite different from the data that you'll confront in an application you want to be robust to that info gap. Here's a project that I worked on a number of years ago with GM. I finished the project and they went broke. I don't know if that was a relationship or not, but there was robustness curves involved here and preference reversals. Military applications, let's move on. We're running out of time. Applications in military intelligence and policy neutrality. This is important that the analyst needs to support decision-making by a higher up person. He needs to do that without actually influencing the decision. The Infogap Robust Satisficing provides a tool for that. Financial securities, yeah, that's nice. Public health, here's an application with colleagues dealing with tuberculosis HIV epidemic in Botswana. The epidemiological dynamics were highly uncertain because of the TB HIV interaction, and we infogapped it to give public health recommendations. This charming little animal over here is an endangered species, a Sumatran rhinoceros. The question is what conservation methodologies are appropriate given our very limited knowledge about this rare animal. Let me wrap up. We've talked about infogap uncertainties, innovations, discoveries, ignorance, and surprise. I've stressed that our ignorance is unbounded. We know a lot, but much more we do not know. We're optimistic. Our models are good and they get better all the time. The trouble is we need to be realistic about the fact that our models are wrong now. We need to make responsible decisions. We need to specify our goals, maximize our robustness, satisfy the goals, and study the trade-offs. Thank you for your attention.
Thank you so much, Yakov, for your talk. I find that really intriguing, actually. I've never heard the Infogap kind of perspective on things, but I know for my work in particular, I'm working in an emerging industry, and I could see how this would be extremely relevant. So I'm looking forward to exploring your work a little bit further. I'd like to open up the floor. Does anyone have any questions for Yakov? The first question that I've noticed in the chat is from Enrique. Would you like to unmute yourself, Enrique?
Yeah, can you hear me?
Yeah, crystal clear.
Yes.
Yeah, thank you for your talk. It was really interesting. I was wondering, in the robustness curves that you showed, they seem to be like very precise and not uncertain at all. So how do you, is there the case that maybe you are not quite sure about that robustness curve, and maybe you have a family of, I don't know, how would you
Right.
model?
Yeah, it's an interesting point. If we go back to, say, Jim Hall's robustness curves. Yeah, the robustness curve manages uncertainty. So in the robustness curves I showed, if I go back to like here, the uncertainty is in the shape of a load function. And the question that we're asking is, how wrong can we be in our estimate of the load function? And the outcome will not be worse than indicated on the corresponding axis. So we're dealing with uncertainty. Your question can be understood as a second order or uncertainty. That is, there can be uncertainty in my uncertainties. For example, in this example, what is uncertain is the shape of the load function. I mentioned there are other uncertainties. There can be uncertainty in material properties of the structure. And in these robustness curves, I'm ignoring that uncertainty. So in that sense, these robustness curves are incomplete or uncertain, if you want. And the way to probe that uncertainty would be to extend the model of uncertainty to include other elements of uncertainty. There are also ways of dealing with anomalous or anonymous, that's the word I was looking for, anonymous uncertainties. I don't know what my uncertainty is. There are ways of infogapping pure ignorance in that sense, rather than focusing in on a particular type of uncertainty. That is, you do that briefly by adding an unknown uncertainty term to your system model. You're not ascribing it to a particular mechanism. You're simply saying, other things are going on, I don't know what they are. And you ask, how wrong can I be in these unknown ways? So yes, an infogap model and the corresponding robustness curve presumes or focuses on particular uncertainties and leaves other uncertainties open for further explanation or further examination. Did that respond to your comment?
Yeah, absolutely. Yeah, thank you.
We have another question from William. Would you like to unmute yourself, Bill?
Yeah, can you hear me okay?
Yep. Hear you fine.
Yakov, very nice to see you. Haven't seen you in a long time. I had a question about the trade-off between robustness and performance.
Bill Overcamp.
Yes,
okay.
yes.
Hi, Bill. Yes, it's been a million years. Okay.
Nice to see you.
Likewise.
Experience says that, and it's almost like we assume it must be true, that there must be a trade-off, going in opposite direction between robustness and performance. But what is actually the assumption that behind that? There must be some assumption, or what type of system would not necessarily require that trade-off, that you could actually improve both robustness and performance. So what's the assumption behind that?
Well, the monotonicity of the robustness curve is a very general property, and the intuition there, of course, is that if you are more demanding in your outcome, you're more vulnerable. More things could cause you to fail to reach that outcome. That can be violated in the sense that the robustness curve can become vertical, and that sometimes happens. When the robustness curve becomes vertical, then that means that you have infinite robustness beyond any given performance requirement. That is, beyond the point at which the robustness curve becomes vertical, you're guaranteed to achieve those levels of performance. So the monotonicity, which is universal, can become an infinite robustness, which is, more than that we can't ask for. Only in situations in which the required outcome is guaranteed for some reason inherent in the structure of the problem. The other way to address your question is, if you change your design, then the robustness curve can move around. If we go back to Jim Hall's example, here we can see that if we compare the green and the the green and the blue designs, okay, green is more robust than blue. So, but they're different systems, okay? So we've changed something in our system, and green is always more robust than blue, at least always more robust when it has positive robustness. Did that address your question, Bill?
Yes, and it is almost immutable that the trade-off is there, except in the rare example that you said, and it then, I think you're saying that it is always the sensitivity of each of one to the other to, let's say, uncertainties or to design. Yeah, that did help. Thank you.
You're welcome.
Okay.
I would like to address the questions chronologically, if you don't mind, Vladik. I think Jorn can be next. Nick Gray's asked me whether he can ask a question. Would you like to unmute yourself first?
Yep. My question will be quick, I guess. So, well, firstly, thanks for talking. Really, really interesting. I feel like this might be useful for a bit of work that I've got at the moment. So do you have sort of a good summary paper or a user guide or something? You may have put it on a slide and I've just missed it.
Yeah. What I suggest is you go to info-gap.com, and that'll redirect you to my website at the Technion, and you'll find lots of stuff. One source there's a link on books. My most recent book is a very slim volume from Oxford University Press, entirely qualitative, no equations there, but it will give you the intuitive background. And you'll see in the engineering page other references at the top of the list that can get you into the math of Infogap. And if you don't find what you're looking for, send me an email and I will try and point you to something more specifically. I'd be happy to. I love getting emails.
Yeah, just to echo what Nick said, I think there's a lot of potential for many applications that I've never come across Infogap myself as well. So I think that resource will be incredibly useful. Did that answer your question, Nick?
Yeah, it did. I'll look on the website.
Great. Vladik, would you like to unmute yourself?
Yep. Thank you very much for the very interesting talk. I think in terms of motivations and everything, you're very convincing. But maybe you can clarify, because you started by explaining, for example, like in climate change, you have 5 different predictions. So suppose now we ask 5 different groups to use your technology, and they will definitely come up with 5 different curves as well. What are you proposing to do in this case?
Yeah. Well, you need to ask what is different in the different analyses. They may have focused on different uncertainties. They may have used different system models. I'm assuming that none of them have made mistakes, of course. They're probably all professors. Professors never make mistakes. Professors never tell jokes either, right? So yeah, the first thing would be to look at what are the assumptions underlying those. And like the first question, one of them may have looked only at uncertainties in the loads, and another only in uncertainties in material properties. And then I have to say, well, what is the situation I'm concerned about? So the differences will be in the underlying assumptions in formulating usually system model and performance requirement. There can also be differences in the performance requirement. One guy may have looked at performance requirement in terms of time to recovery. The other may have looked at performance requirement in terms of displacement between floor 10 and floor 11. So the 3 components of the analysis of robustness, if they're the same, the robustness curves will be the same. If they're different, the robustness curves could be different.
Excellent.
But why will it be the same? Because this is very subjective, right? As you mentioned. There is some uncertainty. You may come up with slightly different curves.
Right. Yeah, certainly one makes judgments. I certainly would never say that an Infogap analysis does not make judgments. It's based on judgments. You have to judge what are the relevant dimensions in your system model, and are you going to model your structure as, if it's the seismic structure of a building, are you going to model it as a cantilever beam or as a 3-dimensional, million-dimensioned finite element? You make judgments, and those judgments, you use the word subjective. That has connotations that are sometimes problematic, but certainly there are judgments.
Okay.
One thing that the and I didn't intend to disguise judgments. One thing that the infogap analysis, like other analyses, allows one to do is evaluate the implications of one's judgments. So that, for example, one might make the judgment that you need to use a very complicated model. But if the robustness of a very simple model is not less or substantially less than the robustness of a very complicated model, then use the simple model and, you know, save your computer time for something else. So that you can use an analysis of robustness to evaluate the implications of the judgments that one makes, recognizing that you make judgments. Absolutely.
Okay, thank you.
Thank you very much for your questions. There's a couple more in the chat, Yakov. I would urge you to have a look when you can to try and answer them if you can. So we're going to move on to our next speaker. Let's thank our speaker again, and we will continue.
So I will stop share.
Thank you.
And chat.
So our next speaker, Dr. Francois Hemez, he'll be speaking on uncertainty, numerical simulations, doesn't matter, and what to do about it. Francois is a scientist at the Lawrence Livermore National Laboratory, where he contributes to assessments of the US nuclear deterrent and supports non-proliferation efforts of the intelligence community. Before joining LLNL, he spent 21 years at the Los Alamos National Laboratory with responsibilities in various programs for computational engineering and physics, and was adjunct professor at the University of California in San Diego, structural engineering department. He graduated from École Centrale Paris in France in 1989, and his doctoral degree in aerospace engineering from the University of Colorado Boulder in 1993. He's been recognized for his expertise in model verification, validation, uncertainty quantification, and decision-making. Since 2001, he's authored 430 plus technical reports, peer-reviewed manuscripts, and book chapters, given 162 invited lecturers, including 9 international keynotes, and taught short courses to 938 graduate students and practicing engineers around the world. So he's got an amazing track record, and I would like to welcome our speaker. Would you like to share your slides?
Thank you, Francis. Can you hear me well?
Yeah, we can hear you crystal clear.
Okay.
Hopefully we'll get the slides working, but if not, we're happy to.
Yeah, we had issues before, so let me see if this times works.
Oh, that's perfect. Yeah,
you see it? Okay.
Glad.
All right, very good. Well, thank you for the kind. Yes.
Just to interrupt, I think you're sharing the screen where you can see the next slide and the timing.
Oh, I'm sorry.
You might want to try to adjust the view. I think if you go on slideshow tab on the top of the PowerPoint, you should be able to do the presenter view, maybe. I'm sorry, not presenter view. Play from current slide, perhaps. Or swap displays, in fact, at the top.
That displays the same?
Yeah, it's still the same. Try swap displays at the top.
Oops. No.
Yeah, that's great.
Better? Okay. All right. Good. Well, let's get started then. Thank you again for inviting me to speak. What I thought I would do is to share some of my observations and thoughts on uncertainty in numerical simulations. And so this will be maybe less broad than what Yakov was discussing earlier, although I will circle back to robustness at the end of this talk if we have enough time. But some of what I do and some of what I think many of you do is to use numerical simulations of various types in your work. And so when doing so, we're confronted with different types of uncertainties. And so I thought I would discuss that and some of the challenges that I have observed and the current issues that I think, at least within my environment, we have, and have a discussion on that. So first of all, this will be the context of this discussion is the work that I've been involved with in the last 25 plus years, which is the context of US national laboratories that worked on high consequence problems for the nation. So my environment is slightly different from what you would find in academia, for example. I wanted to stress that right away. And so we work on things like obviously the nuclear deterrent, but there's a lot of research going on material science, information science, computing, and I'm more particularly involved with topics like non-proliferation. How do we detect or assess proliferation and the risks that may pose to us and our allies, nuclear forensics, bioengineering security, energy security, et cetera, et cetera. So that's going to be the context. What this presentation is and is not, it's as I said, a discussion of uncertainty in simulations. I will keep things at a very high level. There will be no equations or very few equations, very little technical detail. And if you're interested in one particular topic, let me know and I can probably provide with more references. I will try to focus and discuss what I think or perceive are current challenges. I will have a very pragmatic view of uncertainty. So this is not a debate on the merits of various theories. I will go to the box that you have at the bottom left here. Anything that helps solve a problem is welcome and encouraged as far as I'm concerned. So again, very pragmatic view. And I will at the end circle back on uncertainty management rather than quantification, because I think there's an important discussion to be made there. My interest is in simulation-informed decision-making, really more so than uncertainty quantification. So how do we use simulations, including the uncertainty in those simulations, to try to support decision-making, especially when applied to high-consequence decisions? And I'm illustrating this with the well-known image of the disco ball in the lower right corner there, where, for example, if I'm asked to assess what kind of device that is and what kind of risk it may pose to us or our allies, I'm faced with tremendous uncertainty. First, I don't know if this is a real nuclear device or if it's just for a photo op. I have a lot of uncertainty about what it is, what the size is, what the engineering design might be. And so those are the types of uncertainties that I'm talking about. By the time I have distilled down all those uncertainties to maybe not quite knowing what type of steel it is, as far as I'm concerned, the problem is solved, right? Because this is a much more manageable problem than not knowing, what this thing is, even what the intent might be. Okay, so quick outline. I thought I would start with an example of multi-physics applications, typical of the ones that I work with, that I see my colleagues work with, just to illustrate the type of simulations and the types of uncertainties. Then I'll discuss at a very high level uncertainty in modeling and simulation, and then we'll have some discussion at the end. So I picked this example because I think it reflects well what we do at national labs, and this I will refer to as an urban consequence project that attempts to assess and communicate the effects of unauthorized nuclear explosions in urban environment. The reason being that if you have an unauthorized nuclear explosion in an urban environment, the environment itself, so the fact that you are in a city that has buildings, roads, and subways and tunnels will very significantly shape the effects in a way that is fundamentally different than if you were doing a nuclear test in the ocean, which this little insert of the Baker test represents here, or in a desert. And this is very important to train or guide the first responders and how you might position resources to address an event like this. And so that's something obviously something that for which we don't have any data, something for which we cannot do a test and hope we never will have access to such a test. And so it needs to be addressed with numerical simulations. And of course, there's going to be tremendous uncertainties of different types in those simulations. And it's still useful in terms of guiding, finding trends, and being able to help the decision makers and the first responders respond to a potential event like this. So I just have a few view graphs to illustrate the type of simulations that this is. The issue came that our perception of a potential damage from a nuclear explosion has more to do with Hollywood than reality. So I'm showing you here an image of coming from a movies of a depiction of what a nuclear blast might look like. So of course, if that's your perception of such an event and you're a city planner or a first responder, you're going to think, well, I don't really need to prepare for this type of event, because if it were to happen, everybody's dead, it's game over, we don't need to prepare. Well, the truth is that going to those maps that I was able to find on the internet of the actual damage after the Nagasaki explosion in 1945, you see that it's not an isotropic type of damage as hypothesized before. It actually follows the properties of the city. And so having access to that knowledge and understanding the types of effects might help you plan better the response for such an event. So it's really important to understand the distinction here. And so at the national labs, we've developed a series of tools, various codes that can be used to try to do some of those simulations. And so what I'm showing you here is just snapshots of some of the results. You see a satellite map of a city that can be taken, discretized, and so every single, down to the level of modeling every single building, for example, and then that can be used for doing various calculations. At the bottom, I'm showing you some prompt radiation effects, or from neutron radiation or gamma or X-ray radiation. And so you can quantify what that would be. You can overlay that with maps of the US Census population density. So that tells us where the population is located. And then when you convolve those informations with something like irradiation levels, for example, you can then estimate the number of casualties, you can estimate the types of injuries, et cetera, and that's information that might be useful to first responders, again, or emergency room in hospitals. This is another example of showing you a simulation of a release of a dangerous chemical at a location in a city. And so, of course, you see that it's highly dependent on where the winds are coming from. And if you have if you communicate information to first responders coming from those simulations, that might show what the type of response might be. For example, in a case like this, you see a lot of red, which means a high level of contamination accumulating on top of the buildings. Well, if that's indeed the case, then maybe the best response to the population might be, don't go out, stay inside. If your building hasn't collapsed due to a blast or an event like that, it might be safer just to stay inside and wait, because if you go out, you'll be more exposed than if you stay inside. And so those are the types of trade-offs and decisions that can be educated by simulations like this. I think I have one last. Yes. So we can do the source calculation. So given a given weapon, simulate the output, and then look at all the effects, which are much more on a much larger time scales. And so this is showing you examples of some of the effects. There will be urban fires, obviously, from the energy deposited on various structures, but there's also going to be a blast. And so we can simulate the collapse of buildings with a fairly high level of details. You see here on the right side a calculation of a collapse for a building where every single rebar in the concrete has been modeled just to see if you get yielding of the steel and what the effect on the building is. In urban environments, we like to build with lots of glass, and so glass breakage might be an issue. because if you have even a modest overpressure, that will shatter the windows and send all this glass flying through the room, and that will result in tremendous amounts of injuries like cuts and things like that, in addition to injuries due to the overpressure. And actually, simulations indicate that if you have a modest nuclear explosion of modest size in an urban environment, probably 70% of the injuries will be due to the overpressure, so broken bones and glass breakage. And so it's again a very different perception than what I was starting with, which is, well, nuclear explosion, everybody's dead, game over. No, the emergency room really needs to prepare for having a large influx of injuries that will be glass breakage related. And so it's a very different treatment than treating people who have been irradiated, for example. And so that's the type of training, between quotes, that goes on with simulations like this. So that's for the example. And of course, in putting together simulations like this, there's going to be a lot of uncertainty. And I just want to overview this quickly. So this is the world around us. You know, we have nature. We have a little rabbit here doing his going on his business, and that's not the way as scientists and engineers we see the world. This is how we see the world, right? Through equations to model everything. So we put an equation on everything, and of course, if those equations were correct, and if they represented the world, we would be, all we would need is a big computer to be able to calculate those equations in a coupled way, and we would be done, and most of us would be out of a job. Naturally, that's not, we know that's not what happens, because there's imprecision in our understanding of the world. There's a lot of different types of uncertainties out there in how we understand physical processes. And so we have to deal with this uncertainty. The challenge of being predictive is that, one of the challenges is that there's tremendous potential to introduce uncertainty in the models we put together and the simulations based on those models. So there's a lot of environmental variability. Things we manufacture have some finite level of precision. So there's going to be manufacturing variability or assembling variability. If you're trying to put together a complex object like an airplane or a car, the materials themselves have properties that vary. There's a lot of unknown about how energy gets dissipated and exchanged between subsystems in physics and mechanical engineering. So there's a lot of energy dissipation mechanisms that introduce some uncertainty. Initial and boundary conditions are often unknown. If you're thinking of a climate model, for example, it's not quite clear what the boundary conditions might be. Even the initial conditions. Of course, we know the weather of yesterday, but we mostly know that weather where it was measured, which is over land. And we know that what drives the global climate is not so much what happens over the land, but over the ocean and the atmosphere. So we do have big uncertainty in terms of the initial condition. A lot of the times we're going to have to resort to discretization. I'll say more about that in a minute. Which means that we compute over some kind of mesh, and there's going to be some truncation effects due to the particular choice of mesh size to discretize some mathematical operators, et cetera, et cetera. So there's a lot of potential for uncertainty. I will give a very high level overview, categorizing this uncertainty in three broad classes. So first, there's what I would refer to as variability and randomness, the fact that there's uncertainty introduced by things that have an inherent randomness into them. I will not say much about this because I think we have a plethora of well-developed and well-accepted tools for handling randomness. There's the second class is numerical uncertainty, the fact that there's a special type of uncertainty introduced by the fact that we need to discretize the operators that represent our understanding of reality. And then there's model form uncertainty. So there we'll be back to assumptions and the fact we have to make assumptions into how a particular material behaves, for example, which will introduce model form uncertainty. So just a few words on each one of them. The first one, variability, and the fact that it comes from randomness in things like the geometry, material descriptions. That's something that can be addressed very well, in my opinion, using probability and statistics. And so I've got this just one high-level summary here, and we'll say nothing more because I'm sure most of you are much more experts than I am in probability and statistics, and that is the tool of choice to describe and analyze randomness. The basic process is illustrated at the bottom here, where you have a calculation, for example, that has, in this case, an uncertainty about the material property. This is meant to represent crushing spherical floats to try to understand what the ultimate strength is for those systems. And so let's say that the steel, in this case, so the aluminum used to build those spheres, has some variability, and so you can assign a probability law to that source of uncertainty, sample it using statistical sampling, propagate the samples from the inputs through the calculation, and if you accumulate enough samples, you can then use that information to do statistics and estimate what the probability of your quantity of interest might be. And so that's very well known. And I think, again, I don't think I need to say much more about tools that might be appropriate to propagate randomness through simulations. The issue is that not everything is variability. If you look at these two simulations of a drop of one liquid dropping into a different liquid, you see, if you look carefully enough, you'll see some differences between them. And this was results obtained by using two different codes, one from the University of Chicago and the other one from Los Alamos National Lab. And those test problems are extremely well controlled. They start with the same basic definition, the same mesh, everything is the same initial boundary conditions, but yet, even though two different codes are used to solve the same problem, you see that some differences develop. And this is due to the fact that, again, it's not randomness, it's the fact that those different codes are built differently, they're based on different assumptions, and those different algorithms and treatment will develop into differences after some time. And so that's what you see here. So where does that come from? Well, we all know that the engineering and physics codes solve conservation laws. So I don't need to explain what a conservation law is to this audience, but basically trying to solve equations that express the fact that fundamental quantities such as mass or energy is conserved. And so you start from a plain English language that says, for example, that the rate of change of a quantity is simply equal to the difference between what enters and exits a control volume. And then you translate that plain English into equations, and you obtain a conservation law. And what those complicated simulation codes that I was showing you with the urban consequence project, for example, was attempting to do is simply to solve those equations. The problem is that the solutions to those laws are known only for very simple geometries. So think of something as simple as a sphere or a cube or some simple geometry. And so if we want to solve those equations, we have two solutions. We can engineer everything like a simple geometry, everything like a cube. If that were the case, all the cars we would drive would look like a cube, because that's the only way we can compute anything. That's obviously not the choice we've made. Or we can take a complicated geometry like this geometry shown to the right here and discretize it into those simple pieces, simple elemental volumes for which we have solutions, and compute on every single little piece of volume and then put the solution back together. So that's the principle of discretization. We discretize those equations, and that's how we can compute solutions. The issue becomes, of course, truncation, because now the solution which we're trying to estimate, which in this little graphic on the left here is represented by the blue curve. the solution, which is the truth that I'm trying to estimate, is unknown to me, and I'm only obtaining an approximation on the base of this discretization that I've chosen, which here is represented by this series of little constant values over control volumes, delta x, or in this case, control length. And so the quality of the numerical solution I get will depend on the size of this discretization. And that's the second type of uncertainty that I want to briefly mention, is the fact that we have numerical uncertainty, mostly truncation error if you do your job well, but there's other types of numerical errors that have to do with Randolph or with other effects. But I will stick with truncation effects because it's usually the most dominant one. And so again, that's for this type of uncertainty, I will say not much more, because I think there's technology that's been developed, for example, to develop upper bounds here, such as this one I'm showing you here, which says that even though I may not know where the truth is, I can bound the difference between where the truth is and what the computer calculates for a given choice of discretization by this upper bound. So those upper bounds here can be estimated, and that gives you an estimate of how much uncertainty you might have relative to what you compute. And so, so there's tools available to do so. What I want to spend a little bit more time, of the time that I have left on, is model form uncertainty. And what I mean by that is that we have to formulate assumptions to, again, mitigate the fact that we have lack of knowledge, we have ignorance about reality and how physics and the mechanics around us truly behave. And those assumptions will introduce some uncertainty, of course. So take this example of the rocket 5 here. That was the Saturn V rocket that was studied in the 70s. The reference dates that I'm giving you here dates back from 1974. So a long time ago, when engineers back in 1974 surely didn't have access to the computing power that we have now in something as simple as this, right? And so so they had to go from a reality of interest to a conceptual model, and then make a lot of assumptions to be able to simplify this reality into something as simple as maybe a series of beam models here, and be able to compute on that, because that's all the power that was available to them. You can decide on a different set of assumptions and represent this reality of interest of the rocket into something that's a little bit more realistic here, maybe, that uses a different set of equations to represent the behavior of this rocket. Likewise, the graphic on the right presents the same idea, where a lot of assumptions are made to convince yourself that, yes, doing experiments on something as simple as mice might be a good surrogate to study the human genome, for example, because we can't do those experiments on humans, and so we use a surrogate. So there's going to be a whole set of assumptions there to go through, and that introduces uncertainty, because those assumptions have to be decided and chosen. And if one of them happens to be incorrect, then you get uncertainty into the prediction you make. So a simple example here of this of this high school student doing an experiment on a pendulum that probably most of us have done at some point. And we've all known that the dynamics and the oscillation of that pendulum can be represented by a simple equation as the one shown here. And this looks like a nice equation that you can do math with and solve, but there's a lot of assumptions built into this. For example, it's assumed that there's no string tension in the string. It assumes that the sine of theta can be simplified just as theta, which means that this equation is limited to small angles around the position of equilibrium of this pendulum, et cetera, et cetera. So there's going to be a lot of potential uncertainty introduced if some of those assumptions happen to not really represent reality. So that's a simple example here, but in computational engineering or physics, it's the same idea. We make a lot of assumptions. So if you want to use or write a computational code, something like a fluid dynamics solver or a finite element code or a strong motion code or any kind of transport code or et cetera, you're going to have a whole list of assumptions that get built into constructing that code. In mechanical engineering or computational fluid dynamics, one of the first choices is how do you represent a material motion? Do you have a fixed grid through which everything flows that would be referred to typically as a Eulerian grid? Or do you have a grid that represents the material that deforms with where the material is trying to flow? And that's typically referred to as a Lagrangian motion. If you have multiple materials in your problem, do you have a single pressure within a control zone or control volume, which again is this fundamental simple geometry for which you can compute? Or do you have one pressure for each material? So think of this ice cube that I'm showing you on the right side here. This may look like a very simple glass of water with ice in it, but next time you have a drink like this, think about it. This is actually quite complicated problem. You've got liquid, you've got solid. You also have phase change. Eventually, the ice will melt and transform into liquid. Well, how do you handle that computationally if you have a zone that represents your ice cube, and then all of a sudden, some of that ice melts and becomes liquid? So you have a phase change. Do you track the boundary between your ice and your water? How do you do so? How do you approximate some of the operators, such as gradient operators, needed to solve the equations, the conservation laws? How do you approximate something like what generates vorticity, for example, something like this? If you use different meshes to represent different pieces of physics in your problem, you're going to have to transfer state variables, things like densities and pressures and displacements from one mesh to another one. How do you pass information across meshes? Does that preserve your conservation law, or does that introduce some artificial dissipation or advection errors? All those things will creep in to eventually produce the differences that I was showing you earlier with the mixing fluid bubbles. So this is just an example in solid mechanics for representing, for example, the difference between to represent the behavior, the high strength behavior of metals. There's all kinds of equations out there. I'm just showing you 3 of those choices, but there's many more. And whether you decide to compute with the first one or the last one here will produce some small differences in your calculation. And if you are doing a complicated numerical simulation that has millions, if not billions, of those little control volumes, and that you integrate over time, those little errors will build up over time, and that's how you end up with big differences. All those little models, such as the material models I was showing before, are needed to really, at a high level, provide closure on the fact that in a complex numerical simulation, you will have a cascading down of information from the macroscopic scale down to the smaller scales. So you can think of your simulation as being a succession of different of solving different equations here. And within engineering, we are clearly at this level here, right? The macro mechanical level. So we're solving Newton's law, we're solving Navier-Stokes equations to try to simulate how buildings collapse or don't collapse under an earthquake, or how airplanes fly. We're not so much interested in what happens at the sub-level, at the level of an individual crystals or molecular dynamics, etc. So all those choices of models will fill the role of essentially a filter of information, right? They will stop the cascading down of information at some level that is decided by the type of model that you use. So I'm digressing a little bit here, but I'll come back to uncertainty next. Because if you view your numerical simulation as a low pass filter of information, where there is information that you will be able to resolve based on the choices of models and mesh that you use, and there is information that you will not be able to resolve, meaning that it has to be modeled explicitly. If you view your simulation as a low pass filter of information, then the analogy with signal processing makes sense, where much like in signal processing, where you decide to filter out the dynamics of the high frequencies because you don't care about it. Even though you filter it out, you know that those filtered scale will come back and bite you in terms of uncertainty that they introduced at the result scales. And so you have the same, at a very high level, you have the same fundamental dilemma of, well, you decide to, you need to bring closure to this cascading down of information, otherwise there's no end to it. And the type of closure you bring will generate some uncertainty. And so you can ask yourself, is it appropriate? I know we can do it, but is it appropriate to assign probabilities or other types of functions to parameters of a model to describe that uncertainty? Or is that something that makes sense doing, which is what we currently do, or not? Likewise, fundamentally, you're going to have a dependency between the mesh resolution that you choose for a particular calculation and the type of models that you choose to describe the behavior that stops this cascading down of information. And I don't want to get into this because it's philosophical more than anything else, but that's a big concern. So I'll stop here and then use the time that I have left to basically discuss where I think we are and what some of the challenges are that I've seen. So what are some of the current challenges? I think the aggregation of uncertainties of different natures, different types, becomes an issue. I try to, at a very high level, overview the different types of uncertainties. We have parametric uncertainty, randomness, variability, numerical uncertainty, model form. I'm not convinced that we do a good job being able to aggregate those different types of uncertainties. And the solution to some may be to put probability distributions or different types of functions that describe the uncertainty on everything and then have ways to aggregate that. I haven't seen that, at least within the work around me, I haven't seen that being done in a principled and rigorous and satisfying way. That goes into the second bullet as well. Averaging between quotes, put averaging between quotes because I'm not sure I'm using the term correctly. But what I really mean is aggregating different types of models. It's not done in a very satisfactory way. When trying to do it using things like Bayesian inference, for example, it's found that very often the likelihoods do not sufficiently constrain the models. And so if I'm faced with 2 or 3 different models, it's very difficult to be able to make the argument that some of them should be rejected because based on their likelihoods, it doesn't really help me, which then implies that the prior distributions are often deemed to be too influential. So if I start with a prior distribution, what I find at the end of the process is basically it's giving my prior back and it's not helping. And that sometimes leads to cherry picking the data. If a piece of information or a model seems to be an outlier, well, it gets debated and it gets rejected and it gets ignored when in fact this model might be pointing to information that is extremely valuable. And the mere fact that we're not able to reconcile it with the rest of the data doesn't mean that it should be thrown away. And I'm very concerned about that. There's also a very well accepted practice of developing Gaussian process models for everything. And I am very concerned about the quality of those Gaussian process models when they try to approximate uncertainty spaces in dimensions greater than, I'm saying 10 because it's a nice round number. It could be 12, could be 15, but essentially as you have an inflation in the number of dimensions of uncertainty variables you're trying to to represent with those Gaussian process models, I'm very concerned that their quality is just not what it should be. And now you're replacing a very expensive numerical simulation with a poor quality surrogate that doesn't really help you address the problem. Communication of uncertainty, I'll say a few words about that. And then demonstrating confidence to decision maker is also very important. I think more and more decision makers are asking us to demonstrate why we are confident in the answers, or at least in the analysis that we're providing to them. And we still don't have good metrics to try to quantify confidence. So very quickly on communication here, I'll just illustrate that with a little story that I wasn't personally part on, but one of my colleagues was. And the point I want to make here is that sometimes probabilities or the descriptions of uncertainty, I say probability because it's the most commonly used, but I don't want to necessarily put the finger on probabilities. Probabilities can be difficult to translate into actionable decisions. And this example is a high-level briefing to the state officials in North Carolina back in 2011, where the state officials wanted to prepare for the arrival of a hurricane. And so they had a briefing with the scientists who presented their latest and greatest simulations of what the trajectory of the hurricane might be. And that was complete with an estimation of the uncertainty into that trajectory. So the scientists did the best they could to quantify the uncertainty and provide that information to the governor. And I was told that the government sat there and very patiently and listened to the briefing and appreciated the briefing. And at the end of which, she said, well, this really doesn't help me answer the question of whether I should give the order to evacuate. So clearly a disconnect here between the analysis provided by the scientist and the type of information, being able to turn that information into actionable decisions by the decision maker. And again, I'm not trying to blame anybody here. It's not about blame. It's about trying to give you a precise example of this disconnect. And this disconnect I see all the time, not just between decision makers and scientists, but also within different scientific communities. For some of the work that we do at the national labs, we have the scientists or the engineers, people like myself, and we interface with statisticians. And that discussion is sometimes very difficult to be had because we just don't talk the same language. The scientists don't necessarily want to know all the gory details about how the statisticians put together their Gaussian process models. And likewise, the statisticians don't want to know about what we care about as scientists in terms of our simulation. So the exchange of information is very difficult to have. So communication is still, I think, a big issue. I want to just very briefly bring up machine learning because there's an explosion in machine learning technology. It's being applied to everything, and definitely we see a big push in using those tools for everything we do. And I'm concerned that machine learning, rather than solve, might further exacerbate those challenges, simply because machine learning is a wonderful tool. I think it's really going to change a lot of how we do business, but we shouldn't lose sight of the fact that code and algorithms are opinion embedded in code. I think it's a quote that comes from a French philosopher whose name I forgot, and I tried to look it up and I couldn't find it on the web. So I'll just attribute the quote to Kathy O'Neill, who's a data scientist and activist over here. But she said that algorithms are opinions embedded in code, and they tend to repeat our past practices and patterns, and they automate the status quo. So the question of subjectivity in how a code gets put together, I think really needs to be addressed. Does it give us a false sense of confidence? Is the solution into what's referred to as physics-based machine learning? Maybe it is. Maybe not. An illustration here is what some people call explainable artificial intelligence, where we're not just trying to get a machine learning algorithm to give us a solution. For example, what is this picture? What is this animal over here? It's a cat. But also to be able to explain why the algorithm was able to achieve that decision. In this case, it's a cat because it has furs, it has whiskers, etc., etc. Well, it works well for cats and dogs and maybe playing chess. But if you try to apply it to a problem with deeper uncertainty, such as I'm observing trucks here performing a loading operation, and I want to try to understand if this is something I should be concerned about or not, we're not quite there yet. And I'm concerned that with the tremendous advances that we're seeing currently in machine learning, that we're going to lose sight of the fact that it's not computers that should be making decisions for us. It should still remain firmly in the hands of people. Okay, so I've got a quick example here, and then I'll wrap this up. Here, I'm showing you complex numerical simulations of what happens when you form jets. So think of forming a jet, like a shaped charge jet, to go through armor, for example. On the left, you have an extremely complicated multi-physics simulation of forming the jet, ejecting particles at the surface of a metal. And then those particles, you could see that you can do molecular dynamic simulation on them, and they form little filaments of extremely hot particles or atoms. And that's what helps you penetrate through any type of armor, those extremely hot little pieces of fluid. Well, is that discovery of a new phenomenon through the numerical simulation, or is it just basically rediscovering what we programmed into this simulation? In this case, for this phenomenon to occur, you need to let the the material liquefy, right? And if you don't allow the material to liquefy, like in the right side simulation here, what's going to happen is that the material remains solid and you have a totally different phenomenon. And so the answer you get in your code really depends on assumptions embedded into the code. And if you lose sight of those assumptions, or if you don't question them, then no wonder that you'll observe a certain type of, it shouldn't be a surprise that you'll observe a certain type of behavior, but reality might be totally different. So it's all about assumptions. And in the last 2 or 3 slides that I have left, I just want to circle back to robustness, because to me, it's a wonderful way to ask what if scenarios and question the assumptions by asking, okay, what if my assumptions are incorrect? And I changed an assumption in my calculation and redid the analysis. How different would my prediction be? And can I use that to demonstrate the robustness of my decision to things I don't know, which is embedded in those assumptions? It also ties and brings us back to confidence, because I believe that a confident decision, such as an answer or an engineering solution or a design, is one that guarantees a given outcome, even if some of the assumptions embedded in the calculation happen to be incorrect. And so by doing this analysis of robustness, we can demonstrate to the decision maker why we are confident in the solution, because the assumptions were varied, and we run those what if scenarios. So I just have some quick illustration of that. Yakov discussed the robustness function, so I don't need to go into great details about this. This is my simplified view of how to build a robustness function. I started with an analysis that gives you a baseline solution that might be the green point on this 2-dimensional plot of performance versus assumption making, and then construct different scenarios. And those scenarios can be constructed through a numerical simulation. That's what I tend to do, but it could also be constructed without a numerical simulation, just by linguistics. And so you build different scenarios and repeat the analysis for each one of those different scenarios. That's what the gray dots might represent. until the analysis indicates that your performance requirement can no longer be satisfied. And there you got the robustness function. So again, as a metaphor, let's say that you're interested trying to predict the value of an investment portfolio for different scenarios, such as, well, we're in an era of peace and stability and growth, or maybe that assumption is incorrect, and tomorrow we will go into an era of deteriorating economic growth or social unrest, or maybe we'll have a major terrorist attack, or we can have all of those combined. And you can vary those assumptions to go further and further away from where you started from and see what the value of different investment strategies might be with this notional robustness curve. And the graphic here is just a notional illustration, but it makes the same points that Yakov was making with this earthquake building resisting example, for example, the seismic example, for example, where in blue here, the strategy A of investing might initially look like it's not as good as the strategy B, because you start off with less value of your portfolio. But if you find yourself in a situation where there's tremendous deviation from the current assumptions, that strategy might actually be better. So you get this preference reversal. And in terms of addressing uncertainty, presenting uncertainty to a decision maker, I think this gives you a very intuitive tool to communicate, and one that is able to present the information without making the decision for the decision maker. Let the decision maker select whether he or she prefers strategy A or strategy B, depending on their own aversion to risk, for example. So I just have a quick example here, since this is a more engineering and physics community of calculating those robustness curves for a mechanical design. This was a design of a mechanical latch that I did for a company, and showing that one design, in this case in green, design A, is much superior to design B in terms of not only providing performance, but also being robust to the fact that in this early stage of the design, we don't quite know what the material is going to be. We don't quite know what the force levels or the impact levels are going to be that this device will be subjected to. And so we need to be able to be as robust as possible to those sources of uncertainties. And I will just conclude with this, basically reiterating some of the points I was trying to make, that even though we've made tremendous progress in the last 20 or 30 years, managing uncertainty in numerical simulations remains somewhat of a tricky business. Uncertainty is everywhere in those big, complicated simulation. Even though they're very sophisticated, there's still tremendous potential to introduce uncertainty, and not just one type of uncertainty, but uncertainty of various types. The second bullet here is a quote that I borrowed from Yakov. He likes to say that the model the most appropriate to simulate tomorrow might not be known today. And so even if we have more advances in our understanding of physics and computing power, we will still be faced with this basic dilemma that we need to simulate today a reality that we will observe tomorrow. And there will always be uncertainty in this extrapolation. And the last bullet reiterates something that I'm not too sure how to address as a scientist, but I think it's really important, that there is very often difficulties in finding a common language between scientists, analysts, and decision maker to convey uncertainty, and also to convey confidence in the answers we provide to the decision makers. And I think I will stop there. I apologize for running about 5 or 6 minutes late. So hopefully we'll have enough time for questions. So thank you for your patience.
Thank you very much, Francois, for your talk. I think it's, excellent. Raised loads of really interesting points, and I completely agree. I think finding that common language is really crucial to try and basically inform decision makers in a way that we're all speaking the same language. It's a real problem that I found in my research too. Has anyone got any questions? I know Yakov has presented a question in the chat. Would you like to read it out?
I think he's on mute.
Yes, okay. You can't read my lips. Yeah, great talk, and you certainly brought us back down to the troubling world that we live in. I try to avoid the world as much as possible. I have a million questions, but here's one. Better and truer physics will often be more complex and more uncertain than worse and more wrong physics. Because better and truer physics is got all kinds of bells and whistles that are not quite tuned.
Yes.
So the question then is, how do you know when you should use the better and truer physics or the worse and wronger physics when you need to make a prediction? And I would just suggest that I don't know the answer, but it certainly is an innovation dilemma.
Absolutely, and so two things just to reemphasize your point. I think the short answer is it really depends on the question being addressed, and if a simple, less sophisticated model or model of reality helps me give an accurate enough answer, I will always choose simplicity, just because I'm a lazy engineer and that's what the engineers do. Choose, the answer. I'd rather have the answer in 20 minutes than wait 2 hours for it, and then use the rest of the time to go surf the internet and watch cute videos on cats and dogs. So sometimes the simpler model works, and if it works, then great, use it. So maybe a little bit of a provocative example of that would be to use the Aristotle's view of the universe, where back in the ancient Greece, the Earth was at the center of the universe, and then everything, all the other planets would rotate around the Earth. And we all know, and we all seen those models. And the Greek and others after them went through great sophistication to calibrate those models in a way that for over 2,000 years, those wrong models were extremely accurate in predicting the cycle of seasons, right? And predicting the location of planets. Well, if my application is to predict the cycle of seasons, it's perfectly fine to use one of those models, even though they're wrong. Now, if my application is to predict the orbital dynamics of a satellite that I want to launch, it would be a disaster, but it's a different application. And so that's the first part of my answer, is that I would choose the model, irrespective of what it is, which gives me an accurate enough answer. Now, don't get me wrong. I'm not recommending that you should choose a wrong model like the ones I was just suggesting. The second part of my answer would be to say that, yes, more sophisticated models usually have even more potential to introduce uncertainty. I also believe that even though that potential to introduce uncertainty is greater, the robustness to that uncertainty might also be greater. And so by adopting a more sophisticated, complex model, you might actually, yes, introduce more potential for uncertainty, but the effect of every single one of those new sources of uncertainty will be less. Think of modeling the friction between two surfaces, for example. I can model it with a simple Coulomb friction, which depends on basically one friction coefficient, right? And so I will have just one coefficient to worry about, which is that friction coefficient. Or I can try to represent the surface finish and all the little asperities and imperfections of my surface finish, and then do a contact condition and represent that with a much finer description, which will introduce many more parameters for the uncertainty. But those parameters will be much more localized, maybe a little curvature around an area, and the robustness of my final answer to that one parameter will be enhanced. And so there's always going to be trade-off, like you were saying earlier, between the two.
We also have another question from Corrado. Would you like to unmute your microphone and read out your question?
Yes, I noticed in the first part of your talk that you mentioned the different kinds of uncertainty. Some of them are due to some lack of information, or because through modeling you are making approximations of the reality. My question is if in the realm of simulation, interval analysis or interval arithmetic is considered to deal with this kind of uncertainty.
So I'm in abstract, it's difficult to answer. I would say yes. I think that whichever representation of uncertainty you decide to use should be able to describe what you don't know, but no less, and no less and no more. And so if intervals, if some of the lack of knowledge that you face comes in the form of an interval, and you just don't have enough information to be able to put a probability distribution on it, then definitely using intervals or something consistent with intervals is the right way to go. Does that answer? I'm not sure I answered your question or understood your question correctly. So feel free to follow up.
Yeah, well, yes. What I meant is that, for example, in discrete modeling simulation, you are approximating, for example, a complex shape with cubes, with a composition of cubes. And this leads to an uncertainty on the result because, of course, the reality is not made of cubes. My question is if it is a practice to approximate, to represent the uncertainty about the result of the simulation with intervals instead of precise numbers, which may be unreliable. This was my question.
So for this particular case of numerical uncertainty, my experience is that the overwhelming practice, especially in industry, is to do precisely nothing. So you just run one calculation and you do the best you can and you report the result as one calculation. And there's issues with that. Think of doing an experiment. You know, if you go to a lab or in the field to measure something, if you're a good experimentalist, you know that you're going to do some replicates, and then you're not going to report the result of one single measurement, but you're going to report, you know, statistics on your measurement. So maybe the mean value that's measured plus minus 1 standard deviation, or maybe plus minus 3. Just so that, because you know that there is experimental variability, and if you went and repeated the test over and over again, you would measure something differently. It's like, right? The same is true with simulation. If I went and changed the size of my discretization ever so slightly, I would get a slightly different answer. So the good practice is to represent, to try to do it multiple times and try to quantify what that uncertainty is with intervals. And so whenever people can afford doing it, it's expensive, but because you need to do multiple calculations, that's the way it's typically done. It's to represent it as this uncertainty as an interval, which means I don't exactly know where the true answer is. The true answer being, if I could discretize with an infinite resolution, meaning that my mesh size and my time step goes to 0 or very, very close to 0, I would converge to some answer. And so I don't know what that truth is, but I'm going to try to estimate what the difference is between what I can compute and what that truth answer might be. So yes, it is reported as a simple interval with no knowledge of whether there might be a distribution function on that. That's typically not the way it's done.
Thank you. Thank you.
Yes.
So we're about to move on to the discussion, but maybe Vladik, we have time to squeeze your question.
Okay, I'm just the very first thing that you started, estimating how the nuclear explosion will affect the city. I thought it's a done deal because I'm just from my experience in the Soviet Union, at the late 1950s, suddenly all the city building was changed, and it was explained to all of us openly that this is caused by the American simulations when they blew simulated atomic bombs in the simulated city. So before, cities were built like old cities, one house near another, and it turned out that creates all this fireball problems and everything. And so starting then, the new buildings in all the cities was built where the buildings were separated at different angles and so on. And we were taught that this is like a known thing. This is like based on experiments. But what I'm hearing is that you are reinvestigating this area. So is there a reason for that, or why?
I saw. I don't want to claim that that's the only reason, but I saw. I saw this big push. Being at Los Alamos when that happened back. If you remember, Hurricane Katrina, that was in, I believe, 2004 or so, was a tremendous trauma in the U.S. government because of the lack of preparation. We knew the hurricane was coming, obviously, because we have a few days lead time on that. We knew roughly where it would hit, and the government was totally unprepared. And the high level of government said, never again. We just don't want that. And so that launched a whole series of studies on, okay, what else could happen? We don't want to, we have a responsibility to the public, even though an unauthorized nuclear explosion is a very unlikely event. The consequences are potentially so grave that it would just be totally unacceptable to the US public to say, well, yes, we had ways to investigate this, even though it's fraught with imprecision and uncertainty, but we did nothing about it. And so I think it came out of kind of this terror of having another Katrina-like event.
Okay, thank you.
Okay, let's thank our speaker again. Thank you very much, Francois, and we'll move on to the discussion. Someone's written a question in the chat, but I think they'll find that it's extremely relevant to what the conversation is about. So just a little reminder, no biting, no eye gouging, no wrestling or hugging, and no hitting below the belt. Vicious retorts are allowed. And our question for today is, are there other kinds of uncertainty? So that's quite broad, but maybe Yakov, you could start us off with some food for thought.
Kinds of uncertainty. We know an enormous amount. One of the metaphors of human knowledge is the island surrounded by water. If the island represents our knowledge and the shoreline represents our ignorance, as the island gets larger, the shoreline of our ignorance gets longer. So I suspect that we are going to uncover continually, as we become wiser and wiser, new things and new types of things that we don't know. To conclude this wiggling, evasive answer, let me just say that there's an element of oxymoron in trying to taxonomize ignorance. What we don't know, we cannot categorize. We don't know it. But I am confident that there are wondrous worlds out there that we don't know and will present us with vast arrays of surprising challenges to our limited knowledge. Am I off the hook now?
Yeah, definitely. I mean, I think that was I thought that was quite profound, at least. I think you're absolutely right. We can't address what we don't know yet, and it's hard to taxonomize it. Francois, do you have any following thoughts from that?
No, not really. I think you know, I want to resist the temptation of saying that you know, more sophisticated models are always better. They tend to be, and again, I think if you have a choice between you know, an old model or a more sophisticated one, definitely choose the better one, you know, the more sophisticated one. Models do get better. That's true. Whether that also translates into being more robust to what we don't know, it's unclear. I think in general, yes, that's the case, but I don't think it's a general rule, and so I think that I'll stop there.
Yeah, I mean, there's the 80-20 rule where people say that 80% of the results come from 20% of the substance, you know, and we add all this extra fidelity that maybe doesn't yield that much greater accuracy in the answer necessarily. So Scott was the one that proposed this question, so maybe he can chime in with a few of his thoughts.
Well, I knew this was going to come back to bite me at some point. I appreciate what Yakov said about the danger of doing it, but let's try anyway. I mean, my question would be, is the uncertainty that might be well, not general, but in specific cases, in the cases that you've already done, is the uncertainty that you've captured or corralled in an Infogap model, is that just epistemic uncertainty and just aleatory uncertainty, or is there something else, something beyond that that really feels different or requires different methods that might otherwise be useful and sufficient for those two kinds of uncertainty? I appreciate that, you know, the general problem, it's like dividing ice from snow, but there are practical issues, right? So how do we teach about this? I don't think it hurts to teach people that epistemic uncertainty is different from aleatory. Do you disagree?
One of the participants put an interesting question, Enrique, what about moral uncertainty? So if we take a sort of a Kantian approach, categories, I think that there are other categories in which we need to deal with uncertainty, and certainly ethical issues are important ones. I've recently written a paper about ethical problems of uncertainty. And I think that as we move into more humane, that is human affairs issues, there will arise new types of uncertainty. You know, I was, as I was listening to Francois' talk, on the one hand, I was terrified by how difficult these things are and how complex, and even a glass of water with ice. On the other hand, you engineers, you have a very simple life. I mean, there are laws out there. Just apply the physics, for Christ's sake. I mean, if you talk about moral issues, as Enrique raised the question, or other human affairs issues, justice, equality, the types of challenges, some of them being uncertainty challenges, are going to be very, very severe. And I will conclude by saying that at the Technion, we are now beginning to try and embed the study of ethics in a range of engineering courses, so that we're trying to produce engineers that are at least aware of the uncertainties that transcend, and the challenges that transcend the engineering domain. ethics is one and there are others.
So that sounds like a yes.
Yes, if you wanted one word answer, which I guess is what the question requires, yes. So yes.
Well, I mean, that is a controversial answer, of course. We've had people on in this series already that would argue quite differently. For instance, I don't think Tony O'Hagan is disposed, maybe he's on this meeting, but I don't think he would be disposed to even believe that there's an essential difference between epistemic and aleatory uncertainty.
Yeah, probably not.
Sorry.
I mean, that's what
Yes,
you said in his talk, right?
Absolutely. I've had conversations with Tony and other probabilists of strong Bayesians, Jack Good of blessed memory from Virginia Tech, believe that all uncertainty can be represented in terms of Bayesian uncertainties. And Jack and I had a million conversations. We never agreed on anything. But we each felt that we were right. So yeah, there are huge there's huge room for dispute on this. I'm the pluralist when it comes to uncertainty.
One thing that comes to my mind in terms of another kind of uncertainty that might be difficult to categorize would be, for example, the intersection between AI and technology and the human brain, with the human brain being one of the most complex things in our known universe. How would you kind of see that potentially kind of manifesting, how to categorize our thoughts and our feelings into decisions that kind of map into an augmented reality? Or with there's a bit off piece with engineering, but I don't know whether you've thought about that at all. Talking to Yakov based on this kind of Infogap perspective.
Right. Yeah, there was a talk last week at the University of Oxford Center for the Study of War, a talk by a scholar from MIT whose name is Eric Lynn Greenberg, about the use of AI in strategic decision making. And part of the challenge is that you can make AI that's very, very sophisticated. And the challenge that one challenge that Eric pointed to is getting decision makers to have enough confidence in that huge, ugly black box that they will use the strategic recommendations of this AI. And I had then a conversation with Eric afterwards. And his part of his message was we need to educate these decision makers so that the AI box isn't quite as black or quite as opaque. And I agree with that. But the other thing we need to do is make the decisions robust to the uncertainty that the decision maker faces when he looks into that opaque AI box. Can you robustify the AI recommendation to the opacity of the AI process? And that's a question, and someone else has to answer it. But I think that this is a characteristic of many modern computationally based decisions. Certainly much of what Francois was talking about when he talked about talking with the decision makers is how do you get them to manage the opacity of those huge computations that Frankie and his friends do.
Yeah, I had a similar sort of experience as well. I was collaborating on the risk and uncertainty in agricultural production systems, this kind of project working with farmers, developing decision support tools and software. And a lot of the time, they don't want their decisions to be given to a computer and they don't trust it. And even if you did give them the information about the black box, they don't understand it well enough to want to use it. They'd rather depend on their intuition rather than the evidence and the data, unfortunately. But maybe also the scientists are getting it wrong, but they're also struggling to communicate it in the right way. But I don't know, let's go a bit off piste on this question, but just thinking out loud, really. I know there was a question also in the chat from Raymundo Julian, who didn't have a chance to ask his question in response to Francois' talk, but it seems quite relevant now if you'd like to read it out, Raymundo.
Hi. So, sorry, I can turn on. Hi. So the question is a little bit about what to do in practice when expressing this uncertainty. So you have many types of uncertainties, let's say numerical, and probabilistic, and others. And the question is, okay, you have to communicate these results, and you might not want to aggregate all these type of uncertainties in just one. And the question is to a practitioner like Francois, how do you do it? You posted as a question, but I'm sure you have some partial practice that you do.
So yeah, that's a very good question. The short answer is I don't know. I don't know what, first, if you wanted to aggregate, I don't know how to do it. I don't know what the best way is. If you didn't want to aggregate, I don't know how to communicate the answer. And then between aggregation or no aggregation, I don't know what's best. What I've seen people do right now is you start from the best possible case, the best possible model, and then propagate to the extent that's doable, propagate uncertainty of what we believe are the main lever arms, the main in a problem. In a problem, you're going to have potentially hundreds of sources of uncertainty. Think of a complex numerical simulation. You're looking at the flow dynamics around an airplane, and you want to make sure that the plane doesn't stall. You're going to have potentially hundreds of sources of uncertainties down to variations of the aluminum properties used in the plate, variations of the rivets, the flow condition, et cetera, et cetera. But out of those many dozens, only maybe, hopefully no more than half a dozen will really be influential in terms of changing your answer. And so start with the best possible knowledge, identify what this small number of critical variables are, and then propagate that in conventional ways, using probability and statistics. And when faced with different models, then just use, basically what I've seen used the most is some sort of Bayesian averaging to combine, to aggregate different models of different types of uncertainties. So represent everything as a Bayesian type of process, and then just use Bayesian rules to combine that. And I think the reason why that's popular is because, as you all well know, it's a principled approach. There's a mechanism to do, there's a machinery, right? And you just follow the recipe, you'll get an answer. Whether that's the right way to aggregate different models or different types of uncertainties, I'm not sure.
Vladek, did you have something you wanted to add as well?
Yeah, so first of all, I want to thank Yakov and Francois for the great talks. Thank you very much. And of course, my personal answer to the question, of course, there must be, because we've seen a lot of uncertainty, like interval computations, imprecise probabilities, p boxes, and so on, probably, and Yakov's approach, and probably others are coming. But the big question I have is, maybe one of you or both of you can comment on COVID situation. The reason why I'm asking that, and I'm attending many conferences, and very often there are people who are kind of using some statistical or other approaches to heavily criticized decision makers, because it's true. I mean, this is the typical situation when people had to make decisions under severe uncertainty. In different countries, they made different decisions. And I'm not just mentioning Sweden versus other part of Europe, but also like social distancing. In some places, it's 2 meters. In some places, it's 1 meter. And many people are claiming that if the government would listen to their supposedly correct approach, things would be better. What do you all think about that? And do you have any kind of ideas of, should we believe these researchers who claim to have known better?
Just a very brief response. I have written some things on COVID. I gave a talk at the Society for Medical Decision Making a few months ago. There are a few papers on my website in the medicine page about COVID, because this certainly is, we are living in an infogap world. And I don't want to say that I'm happy with COVID, but I'm happy with the infogaps, if you'll understand what I mean. So questions, for example, about how frequently one should test, and many other questions. These are very much infogap questions, and we need to make decisions before we have thorough scientific understanding. And so we need to satisfy our performance requirements and maximize our robustness to our ignorance. That is my methodological recommendation for COVID and also for other areas.
Yeah, so quickly as well, I think the COVID pandemic is a wonderful example, because it really integrates, all the issues about uncertainties. We've got tremendous epistemic uncertainty about this, right? Because we don't know what the virus is going to be. We don't fully understand what this virus, how it works, what it does, what the effects are. We don't know what it's going to do next. So I would think that those are epistemic types of uncertainties. At the same time, we have tremendous data, because this has been going on all over the world. So we have, I'm sure, gigabytes and terabytes and gigabytes of data, right? Statistics with which we can do statistics. So it's a more conventional type of uncertainty as well. And as knowledge increases, what was yesterday epistemic now becomes aleatoric in a sense, and maybe vice versa too. I don't know. We've got different types of uncertainties. There's clearly the moral dilemma, moral uncertainty. How do we vaccinate? Do we vaccinate the older population first before the first responders, or vice versa? And we've seen all kinds of different strategies. And so how to face with a case like that, what seems to make sense to me would be to shift the debate away from trying to quantify, what does it even make sense to try to estimate a probability density function or a p-box or intervals about, what the virus is going to be, or how many people are going to be infected given some course of action, 20 days from now. Or does it make more sense to shift the debate more towards decision making, like Yakov was saying, and be able to quantify or say something about how robust are we if we decide on a given course of action for vaccination, for example? How robust are we? So are we going to meet our objective of protecting enough of the population, given what we don't know, given the fact that the virus could still mutate, given the fact that people might not accept the vaccination as much, et cetera, et cetera. To me, that's what makes more sense, as opposed to trying to describe the uncertainty and quantify it in some way, until we get more knowledge, which then allows us to do that.
Thank you. Can I comment on this? It just reminded me, because in Russia we had, I don't know, it was probably outdated impression that there were two medical schools, the German and the French. The French medical school was more scientific, when a patient comes, they first try to test and figure out what's wrong with the patient. The German school at that time would immediately try to cure the patient and don't bother to figure out what's happening. For example, give a big dose of antibiotics or something. And so I think what you're recommending is more like a German type decision in this case.
Having French origin, of course, I want to be as Cartesian as I can. but yes, definitely, especially faced with those high consequence decisions, where we really need to do both. We need to be able to understand what the problem. The correct answer is yes. Let's try to understand what the problem is. It's just sometimes we don't have the luxury of understanding what the problem is. And I think that's to a great extent the what we're facing with this crisis. We can't just tell the populations, well, give us 3 years, and then in 3 years we'll get back to you and we'll tell you how to deal with this virus. We just need to do something now, and that's of course there's going to be some incorrect decisions, and that's just what we have. So
thank you.
If I could add just one brief comment here, we are in the case of COVID, which is an evolving disease. We are facing what Karl Popper and independently GLS Shackle, who Shackle was at Liverpool, if I'm not mistaken, GLS Shackle called indeterminisms. Indeterminisms in the Shackle-Popper sense are things that we cannot know because they are not yet determined. We cannot know the severity of the virus 6 months from now because the virus 6 months from now does not yet exist. In that sort of indeterministic context, trying or withholding action until we understand the physics will cause the patient to die. So we need to be practical, as Francois is with his high consequence decisions. I would just conclude by quoting Boltzmann, who said, "There's nothing more practical than theory." Boltzmann, of course, was a theoretician.
So I think we're coming to the end of our discussion anyway. I don't know whether, Scott, you'd like to make some closing remarks based on anything that everyone said.
Yeah, I can't think of anything smart to say.
Me neither.
So maybe I'll say a few dumb things, but I'm not sure how. I mean, it almost feels bewildering, right? I mean, there's some talks you listen to and you think, I know what to do, but Francois especially has sort of scared me about the future and about our ability to make it. I mean, being practical seems like good advice, but I'm not sure it's a path, if you know what I mean. I'm a little.
I didn't mean to scare anybody. I apologize if I did. I just wanted to, to show a different perspective.
Yeah.
But we've made tremendous progress. Airplanes don't fall out of the sky usually, right? I mean, we can trust the models. We made tremendous progress in the description and understanding of uncertainty. We have tools. So I think this is more than being scary. This is a golden age.
Well, that's interesting. You would say that. Bill Oberkampf, when he spoke, he sort of he explicitly gave a list of dramatic engineering failures, and implicitly attributed them to failures of uncertainty analysis. And I think we all are sort of keeping our own lists of such things. And of course, there are always engineering failures. That's typically how the field progresses. We learn, oh yeah, you shouldn't build that pyramid quite so steep, and you really should put some more pins on that skywalk. It turns out, and so maybe that is the price we pay for learning about how to do this better. But it is a little shocking. I mean, should you asked before rhetorically, should the governor trust the scientists? And the answer is no. No, they shouldn't trust the scientists. You should always be doubtful, right? The question is, how can we modulate our doubt to be reasonable and not to be hysterical, I guess, is the always ongoing question for me. How do I become a skeptic but not a juggalo, who rejects science altogether?
Yeah, I completely agree, Scott. And to echo that, I watched this excellent TED talk called Trial, Error, and the God Complex, and they gave numerous examples of when they've asked experts for their advice on how to deal with a certain disease or how to design a certain nozzle, and they put all the experts in the room and try and come up with a solution. And more often than not, they're completely wrong. And the way that they figure it out is just learning from their mistakes and trying many different approaches.
There's that great
conversion to a solution. Sorry?
I'm sorry, I was just going to tell a joke. That there's that great joke about the definition of an expert. Some people think it's someone who's come from more than 50 miles away, but no. The real definition of an expert is someone who's made all the mistakes already. Their career has been so long, they've made every single mistake it's possible to make, and so it's easy for them to see when you're about to make one. And it may, that's the terror, that I was talking about before. It's we haven't figured it out. We're just learning what not to do.
Yeah, exactly. And I would love to see, say, politicians, for example, to put their hands up and say, we're not sure what the right solution is, but we're going to try a bunch of things and see what works and what doesn't work. And I think that would be, to not shy away from the uncertainty, but to kind of dive into it more, would actually be more of a philosophical way to deal with some of the challenges we face. Just to give an example with the COVID situation, for example, I know that Japan tried the 10 p.m. curfew like we did, and it didn't do anything. It made the situation was still really, really bad. So they changed it to 6 p.m., saying, well, if 10 p.m. doesn't work, try 6 p.m. And that had a massive impact in reducing it by 80% of the transmissions over there. But that's one economy that might necessarily work over here. But it's important to experiment with things to see what things work and what doesn't work.
Yeah, I would love to see that happen in America.
The problem with that, Francis, is there's the fine line between saying, oh, well, the vaccine program is a massive scientific experiment on the whole population, which it is. And if you, from anybody from a sort of sciencey background can see that, but try getting the Prime Minister to say that and not having all the anti-vaxxers up in arms immediately.
Yeah, I mean, you're right. It's not just a political thing. It's a cultural shift that people need to learn how to embrace uncertainty more openly rather than running away from it.
I think only Chairman Mao had the courage to let 1,000 flowers bloom. He knew he could call those flowers whenever he wanted.
So does anyone have any last points before we wrap up?
I would like to thank Scott for organizing this, and Francis also for organizing and running it. It's been very stimulating. Thank you very much.
No, thank you. And thank you, Francois, as well, for excellent presentations and really stimulating some really interesting debate. It's an absolute pleasure.
Thank you all. Yes.
Thanks to all the attendees as well. Thanks, everyone.
So hopefully, if anyone can make it to the 3rd of March, I'll just remind us of the time. I think, oh, got to go back a few. 3rd of March at 3 o'clock, we'll have Daniel Straub and Louis Crespo, whose talks I'm really excited to see as well. So hopefully see you all there and have a lovely evening.
Bye-bye. Good night.
Bye.
You.